Hello guys. Can you hear me clearly? Can you hear me clearly, everyone? Can I get a quick yes? Yeah, I hope everybody is able to hear me. Perfect. So, yeah, we'll just start in 2 minutes so that everybody joins. I'm sorry for 2 minutes delay. Okay, perfect. So, guys, today we will be discussing about transformers. We'll understand the full in-depth intuition, you know, we'll understand the architecture, and again, so second part of tomato project, don't worry, it'll come. It'll be in it'll actually be in what to say, in Google Colab. I'll just try to upload that, but I hope everybody is super happy that we are finally doing this transformer session. Now guys, transformers, before I heard about transformers, it was somewhere around last year. I was planning to learn transformers. So if I talk about attention is all you need research paper. Okay. First we'll go to this research paper. Trust me, it has taken many days for me to learn this thing. And again, continuous, you have to actually learn many number of times. And yes, after transformers we will be also understanding about BERT in the other live session. Okay. So will there be a practical implementation of attention transformer in this session? Not in this session. We'll just understand the whole architecture. Later on, there is a library which is called as Hugging Face. We will be discussing about that probably in another live session. So let's take it one by one. But I really want to dedicate this whole thing to the researchers. They have done some amazing work. I don't know, like they have a lot of patience when they usually implement this many things. Continuously they are working. They're working in sharing knowledge and all. So attention is all you need. In this session we'll be covering attention is all you need, and definitely a good hats off to all these researchers. For this amazing research paper. I could not understand much of the research paper initially, but again, hats off to them. They have done some amazing work. So this is the whole research paper. The research paper link is given in the description. Okay. And if I talk about this research paper, it was basically in collaboration with researchers or scientists from, the developers from Google Brain. You can see Ashish Vashwani, Noam Sazir, Nikki Parmar, Jacob Utskoret. I hope I'm pronouncing it right, guys. If I'm not pronouncing it right, I'm extremely sorry about that. Leon Jones, Aidan N. Gomez, Lucas Kaiser, and Ilya Polosukin. Okay, so you can see that this was a collaboration between Google and the professors from University of Toronto. Um, and I don't know Ilya Polosukin, where does he actually work? I'm extremely sorry about that. I tried to find out some information, but I could not. And this is the whole architecture of the transformer model. And definitely, just by reading first time this research paper, trust me, you will not be able to understand, because we are not okay. Because at least I am not that intelligent. By just reading this research paper, I'll be able to understand, because there are a lot of complex equations and all. But I definitely, initially when I saw this, I told, okay, I'm just going to skip this because I'm really not able to understand. I just completed around 10 to 20%, and then I was trying to follow this. It really messed up in my head. Um, and you will be able to see that apart from this research paper, I was able to understand this research paper. Okay. If your YouTubers do a streaming by mistake, please warn them through LinkedIn. If our YouTubers do a streaming, okay, I've never done that. So, okay. Now, I really want to give a very good hats off to the people over here. Apart from that, this whole video is basically credited to Jay Alammar. So he is this guy who has written this amazing blog on transformers by giving in the much more animated way, you know. So trust me guys, after reading this, I went to this research paper in short. Okay. Initially I tried to read this research paper, nothing. Hardly I was just able to cover till here. And after seeing this architecture, I was like shocked what is happening, because till now, whatever we discussed about RNN, LSTM, RNN, encoders, decoders, and many other things, right? It was pretty much simple, because from seeing the research paper, the concepts I was able to understand. But definitely, after seeing this, it was very, very much difficult. But thanks God, we have again we have Jay Alammar. So he has written this amazing blog. This blog link is given in the description, guys. We are actually going to discuss about transformers through his blog. And Jay also has a YouTube channel. Okay. So in this YouTube channel, he has uploaded about GPT-3. You can see how GPT-3 works, easily explained with animation. So definitely, I liked his teaching a lot. He has, I don't know why he has so less subscribers, instead because he may have uploaded just 3 videos, but trust me, he has done a whole lot of things. If you read his, and there is also one more thing, right? So there is a whole this URL which is called as jalamar.github.io, where he has actually put up a lot of articles, a lot of amazing articles, which I was actually going through, you know. This is one of the article that is illustrated transformer. And guys, again, I'm telling you, the whole credit of this session, you just think that I will not be able to take this session without his blog, okay, Jay's blog. So please make sure that you subscribe his channel. The link is in the description, because you'll be seeing some amazing sessions, amazing blogs from him, I think, in the future as you go ahead, because he's already set up his whole you can see this is all his github.io page, you know. And recently he had also updated this, how GPT-3 works with visualization and animation, I think. So this will be pretty much amazing if you just go through this. So what we'll do is that, first of all, we'll go through his blog, okay, and then we will go through this this research paper, with which you'll be able to understand in a much more pretty much easier way. Okay, so let's go ahead and let's start with the transformers. And remember guys, please, again, the whole credit goes to Jay for this amazing thing. You can also follow him in this github.io. You can actually follow his YouTube channel. Just subscribe his YouTube channel. The link is given in the description. Okay, perfect. So are we good to go, everyone? Can I get a good go ahead, so that you are fine that we shall start this session? Yes, I hope everybody. So it's okay, guys. I really admit to people who teach well. You know, I tell them, you go and subscribe the channel, because you will be able to learn a lot. Not only Jay, but many people, right? So, so shall we start, guys? Can I get a good go ahead, so that we will start this whole session, and then we will we'll go through it, you know, line by line, step by step, and it'll be pretty much amazing. Okay. Okay. So many people are saying go ahead, go ahead, go ahead, go ahead. Yup. Okay, guys. So first, what we'll do is that sometimes if you really want to understand this whole architecture, just follow his blog. Okay, you just have to read. It's in very, very simple words. You'll be definitely able to read it. But I will make something more easier by just telling you how this actually works. But after finishing this, okay, after finishing this, I would like to request you, please go through this particular blog. Read it from start to end. Okay. So guys, transformers. What is the use of transformers? Let's start with this simple thing. So this is my transformer. This whole transformer. Just consider this like a black box. And right now we are converting a language from, we are converting sentences of one language to the other. So this probably is French, and we are trying to convert this into English. So this is the black box model. So usually we say that machine learning or deep learning models are just like black box. We give some input, we get the output. Fine. Right. Now, after going through this, we are actually going to go to the next section, this section. Now inside this, okay, and remember guys, for each and every step, there is some wonderful explanation that is given. Okay. So again, guys, all this GitHub link, all this link is given in the description of this video. So please make sure that you go over there and try to access it along with me. So we'll learn together. I know you may have learned it some or the other way, but let's learn with Lib. Let's see how we will learn. Okay, we've learned together. Over here, if I miss some points, you can also tell me. Okay. Now, guys, so this is a transformer. We are considering transformer as a kind of black box model where we give one input and we get the output. In this case, we are giving an input of sentences in one language. We are trying to translate into another language. Right, done. Now, in the next step, what is present inside this transformer? Okay, what is present inside this transformer? It is simple. Whatever we have learned about encoders and decoders. Okay, so this is the thing that we have inside this. We have encoders and we have decoders. In the encoders, you can see that we are giving some input, which we are actually giving in the form of French sentence, and then we are actually getting the output. Okay, so we are actually getting the output over here. Now, when I'm giving this input in the encoders, and then some processing will happen inside this. Right now, again, I'm telling you, let us consider this as a black box. Then we'll go and understand what is present inside that. Okay, so the input is given to the encoders, and then you hope already we have discussed in our previous session how encoders and decoders work. And in this decoder, we get the output. So you can see over here French and over here English. So G, Suis, Etudiant, I'm sorry, I don't know French. So this is getting converted as I am a student. Okay, perfect. Now let's go inside this encoders and this decoders. What is actually present inside this encoders and decoders? Okay, so let's go to the next step. Now, this encoder, now I'm going inside encoder and seeing what it is. Okay, so now from this blog, it basically says, and this is an amazing blog. It is being compared along with this research paper. And this research paper also, we'll go and have a look. Okay, so inside this block, inside this encoders, right, you have multiple encoders like this. Okay, and you have to remember the count, guys. One important thing over here is that the count over here, let's see. Okay, so if you go and see this, okay, the count of the number of encoders, okay, sorry, this number of encoders is basically 6. Let me just take some other color. Okay, let me just take some other color and let me increase the thickness. Okay, I'll just, so the encoders that are actually present are 6. 1, 2, 3, 4, 5, 6. Now the question comes, why 6? Okay, according to this research paper that you see in the right hand side, that is attention is all you need. This research paper, it says that they had tried with different number of encoders. Okay, so but by selecting 6 encoders, it was giving us good results. Okay, so it was giving us good results. Right, fine. Now inside this encoder, this is one. Inside this encoder, inside this block that you see, right, we are having 6 encoders, and then probably in the decoder also we have 6 decoders. Okay, again, guys, you can change this value. Okay, this is a kind of hyperparameter. You can say like this. This is a kind of hyperparameter, and there are a lot of hyperparameters that are going to come up in this session. Okay, usually whenever you imagine with respect to the number of counts in hidden layers, number of nodes in hidden layers, you can consider that as an hyperparameter. Always the accuracy may change based on the change of that particular value. Okay, now in this case we have 6 encoders and we have six decoders. Okay, so we have 6 decoders. Now it is very simple. In encoder, this input is going. Okay, then something will happen inside this, and finally all this particular value is given to the decoder, and here I will be getting an output. Okay, so here you're taking this as an input and you're taking this as an output. This is pretty much simple. Everybody clear with this much? Everyone? Just by seeing this blog, I think you'll be able to understand. Guys, are you everybody clear with this? Any questions with respect to this step that we have? Please do let me know. I hope everybody's clear. Can I get a quick go ahead? Just give me a thumbs up, guys. I'll just give you 2 minutes. Till then, I'll drink water. Yeah, everyone? All good? Guys, you there? All good or not? Yeah? Okay. Now coming to the, okay, no sir, what no, what happened? See, this is very simple. This is your black box model. I don't know, like if you're having problems in understanding this, then I don't know how you'll understand the future part. So here, encoders is there and decoders are there. This encoder is basically represented by this 6 single encoders. Okay, I'll tell you how the encoders work and everything. We are going from the top level, right? And then this output of the final encoder is given to the decoder of given as an input to every decoder. Okay, how the words are encoded, we will try to understand that. Okay, so here is our input and here we get the output. Now let's see what is present inside this encoder. Okay, what is present inside this encoder? Because inside this encoder, you know, there will be something happening. Okay, so let's go to the next step. So this encoder, now I'm going to take it over here. Now inside this encoder, there are two things. One is self-attention and one is feed-forward neural network. This feed-forward neural network is an example of artificial neural network. It is just like that. So we are going to consider this feed-forward neural network. And what is this self-attention? Now this self-attention is completely derived from something called as attention is all you need. Okay, and this actually plays a very, very important role. Okay, again I'm telling you, self-attention plays a very, very important role. Okay, now let's see. Now we have understood that it's very simple. See guys, this is my transformer. I got my encoders and decoders. What is present inside these encoders? There are multiple encoders like this. And there are multiple decoders inside this, right? This encoder takes an input, all the processing will happen inside this. Then the output of the final encoder will be given as a input to all the decoder, and we finally get an output. Okay. Now what is present inside this encoder? The thing that is present inside this encoder is again two separate layers. One is self-attention and one is feed-forward neural network. What is the difference between attention and self-attention? I'll just come to that. Okay. I'll come to that. Okay. So self-attention and feed-forward neural network. Now we'll try to understand what is self-attention. Okay. And guys, always make sure that as I'm going, just if you have time, just read all these particular statements. Okay. That is how I'm actually explaining. Now, finally, let's take an example. Let's take an example where I have one encoder and one decoder and how these things actually happen. Okay. So here you can see inside the encoder, you have self-attention layer and feed-forward. Okay. Now let me see what is the input that goes to this encoder, because here we have seen some input is going, right? Some input is going over here. G suis étudiant, right? This input is basically going. Now what is this particular input? This input is a text, right? This text. Now that input is first of all converted into some dimension. That input is converted into some dimensions. How it is converted? If you have an input text, how do you convert that? By using an embedding layer, right? Using an embedding technique. It may be word to vec, it may be other techniques, right? So in this particular case, this particular said word from that sentence is getting converted into some vectors. And how it is getting converted into some vectors? Based on this particular research paper, they have used word to vec. Okay, so they have used word to vec and they have converted this into a vector of what dimensions? Here you can say that they have specified a vector of size 512. Okay. Now why 512? Again, it is a kind of hyperparameter. Okay. Again, it is a kind of hyperparameter based on the research paper. See guys, this research paper is not written in 1 or 2 days. They have explored it for I don't know how many years, but I think this research paper came somewhere around 2017, I guess. I think it has come somewhere around 2017. Okay, and I have just read it at 2019. Okay, 2019. I think the month was somewhere around July August month. I was actually started reading this. Okay, so again I am very much late because understand, because as I was working and after I started uploading videos on YouTube, so I started focusing more on some advanced concept. Okay, so I say that YouTube has actually helped me to learn more. Now each and every word we are using word to vec and we are converting into some dimensions. Okay, this is just like a vector of dimension 512 of size 512. Similarly, this word will also get converted. Similarly, this word will also get converted. So whatever input we are giving over here, this will be first getting converted into these vectors of 512 dimensions. Just understand in this particular way. And if you don't know about word to vec, if you don't know about embedding techniques, just go and see my deep learning playlist, guys. I have uploaded video on that. Okay. Now the next step. Now after this is getting converted into vectors. Okay. Now this is passed to the self-attention layer. Okay. This is passed to the self-attention layer. Okay, and as it is, what happens inside the self attention layer, we will understand that in the upcoming steps. Don't worry about that. Okay, so we will try to understand that, don't worry about it. Okay, just imagine that we are giving one kind of vectors to self attention layer, and remember, these words will be given not one at a time, like how we do it in RNN, right? In RNN, in the x-axis, we basically have timestamp, right? So if I consider this, right? In RNN, this will be my x-axis, right? So this will be my timestamp. So here, I will not be giving based on timestamp, but here, the inputs will be given, all the inputs will be given at the same time. So parallelly, all the inputs will be given. Okay. So what do I mean by this is that whenever I am trying to execute this, suppose if I give 3 words, so these words will first of all get converted into 512 vectors dimensions. This word will also get converted. This word will also get converted. And this all inputs will be given all at one time. Okay. This is the amazing thing. Guys, trust me, I'm able to learn this whole thing. Attention is all you need, and about transformers and BERTs because of Jay. Because he has actually given this in an amazing way. Trust me, by just reading this research paper, I was nowhere satisfied. I had just half knowledge, okay? But just by reading this statement, I was able to understand this, okay? So this particular words has got converted into word to vec. So vectors of 512 dimension, and this is basically passed to the self attention. And one point you have to remember, all the words are passed parallelly, okay? All at one time. Then you'll be getting some output like Z1, Z2 and Z3. Now how this self attention model works and how these vectors is actually created, we'll try to understand that. Before that, what is self attention? Okay, we need to understand that also. Now what Jay has actually done is that instead of taking 3 words, he has just simplified the diagram with 2 words. Okay, with the 2 words. And you can see that after this, it goes to the feed forward neural network. Okay, after this vectors goes to the feed forward neural network. Okay, now if I go and see the feed forward neural network, this will be a separate feed forward neural network. So here what he has done is that he has basically simplified this diagram, and he has now basically what he has done is that he has basically used one self attention layer, and over here he has drawn 2 feed forward neural network, since each and every words are going parallelly. And here he has just taken 2 words. And remember guys, this is my second encoder, because the output of the feed forward neural network will be going to the encoder 2. Okay, it will not be just going to the encoder 1. This will now go to the encoder 2. So here you will be able to see that the output, that is R1 and R2, that is created, is going to the encoder 2. Now we'll try to understand what exactly is self attention and what it is exactly. Okay, now self attention has higher level. So he has taken this example. The animal did not cross the street because it was too tired. Okay, now he asks a simple question: what does it in the sentence refer to? Okay, whether it refers to the street or whether it refers to the animal. Because remember, based on this right, it will be converted into French. Suppose if I am trying to convert this into French, this will be getting passed over here, right? This will getting passed over here in this particular input, right? It will be converted into word to vec, right? So based on this what should be your output? Okay, what should be your output? And what this self attention basically says that it will be giving the output based on what this is basically referring to. Okay, what this is basically referring to. Based on that, it will create these vectors. Okay, so here it is very, very much clearly written. You can see that the animal did not cross the street because it was too tired. What does it in this sentence refer to? Is it referring to the street or the animal? It is a simple question to a human, but the algorithm cannot understand this, right? But the algorithm cannot understand this. So how do we make the algorithm understand that whenever this actually goes, it is basically referring to the word animal. Okay, and this can also be referring to too tired, right? Right? To the tired word and to the animal word. It can also refer to multiple words. So guys, I hope everybody is understanding. Can I get a quick go ahead, guys? If you are able to understand till here, everybody is able to understand, right? Because now we are trying to understand the maths inside self-attention. How does it actually work? Guys, can I get a quick yes if you are able to understand? Yeah, guys, just a quick go ahead. Word to vec, I've already made a playlist. So guys, can I get a quick go ahead if you are able to understand? Yeah. Is it interesting? Okay, perfect. Okay, guys. So thank you. So all the 6 encoders are the same, right? Yes, all the 6 encoders are same. Inside, you'll be having self-attention and you'll be having a feed-forward neural network. But remember, this output after the first encoder will be the output of this. It will again, this input will not be going over there. Okay, I'll talk about that also. Okay. Yes, Vasant, he has structured it amazingly. So I'm telling you, right, this whole video credit goes to him. I've understood transformers because of Jay. Okay. Okay, guys. Now the next thing, what we are going to do. Okay. Now let's take this particular example. Okay. Now when I say self-attention, whenever I will be able to give this as an input, I should be able to get the vectors which is specifying the importance of word like animal or tired. Okay. So here you'll be able to see that in one of the attention model, and this is just a diagrammatic representation. Okay. So here you will be able to see that these words that you have like the, animal, cross, this. Now here, when you are giving to the self-attention model, this it word specifies or provides the importance to animal words. How it is specifying? Because you can see the darkness of the line, right? The darkness of the line. The line is too much thick in animals. Okay. And you'll also be seeing that there is one problem. It is not able to specify tired word also properly. But we'll try to see how to fix that and all. But just let's go ahead and try to understand how does this self-attention model work? How we are able to give the importance to other words like animal whenever the it word is given over there. Okay, we'll try to understand in this self-attention. Okay, now let's go. Now self-attention in details. Now what will happen? First of all, we have this input. Okay, this input is basically my word. This will be given in parallel. We have converted this into 512 dimension vectors. So here you can see that I have this x1 vector, I have this x2 vector. Okay. Now the first step that usually happens is that we will be creating 3 weights. Okay, 3 weights, and this weights value will be randomly initialized. Because remember, this weight value will be changing based on your back propagation. If you remember, in back propagation, what will happen? First of all, your loss value will be calculated at the end of the decoder. Then your whole back propagation will happen, and then the weights will be getting updated. So they are actually creating this 3 weight parameter, WQ, WK, WV. Okay, we'll just discuss about this, what is queries, key and values. Now what will happen is that this vector, that is x1, it will multiply by WQ. Okay, so let me just try to show it to you. So here you will be able to see that in this step, this vector, right, will be getting multiplied by this vector. We will be getting Q1. Okay, remember, this is my 512 dimension, and this vector will also get multiplied by this, and we will be getting Q2. Okay, and this will be this one, and this we know that these are 512 dimensions. The number of dimensions that we will be getting with respect to this is 64 dimensions. Okay, 64 dimension. That is what it has been written in the research paper also. So that way, this particular vector, this particular matrix or weight matrix will be created. Okay, so WQ. Now similarly with respect to WQ and WV, like why it is getting multiplied? Because we know that formula, right? Input multiplied by weight, added a bias, and then we activate. That is how ANN actually works, right? We take the input parameters, we multiply with the weight, and then we add a bias. On top of that, an activation function is applied. But in this case, we are just taking this input, we are multiplying with W of Q, we are getting this queries parameter. And this query parameter will be 64 dimension. Similarly, we will take this x2 will multiply with this. Okay. So this weights and this is getting multiplied, and we are getting this. Okay. Now, similarly, what will happen with respect to keys? Again, this x1 vector will get multiplied with W of K, and then I will be getting this key 1. Okay. Similarly, this x2 vector will get multiplied by WK, and we will be getting K2. Okay. So this multiplication is also happened, and similarly values, how we will get this multiplied by your this vector, and this multiplied by your this vector will be actually helping you to get v1 and v2. So did you understand this, guys? I will just mention this at my step 1. Okay. So step 1, you can see that what has happened, two things have happened. First of all, word to vec embedding. Okay. Word to vec embedding. It has converted vectors in 512 dimensions. Then this multiplication actually created your queries, keys and values. And this is basically 64 dimensions. So how WQ is converted into 64 dimensions? Remember the shape of the weights that is taken. If you multiply a 512 dimension vectors into this, you will be getting a 64 dimension. Again, I cannot go and internally say you that how you can visualize this. This is just given as an example. Okay. I hope everybody is clear with step 1. Just tell me, guys. We will go now to the step 2. Everybody clear? Shall we go with the step 2? Why 64 dimension? Again, I'm telling you, this is also considered like an hyperparameter. 64 dimension, 512 dimension is taken as a hyperparameter. Can you change it or not? Yes, you can definitely change it. Okay. Okay, perfect. So everybody is clear. I'm going to rub this and go to my step 2. And again, amazing diagrams, guys. All are amazing. You just have to read. Any lame person, I think a college student will also be able to understand who know matrix multiplication. Okay. Trust me in this. Now the next step. I got my Q1, K1 and V1. Okay. For this word, I got my Q1, K1, V1. For this word, I got my Q2, K2, V2. Okay. I got my Q2, V2, K2, V2. Okay. Why query keys are getting created? I'll tell you why query keys and values are getting generated. Everything will make sense as you go ahead with this block, guys. Everything will make sense. Okay. What is WQ, WK, WV? These are the metrics. These are the weights for generating queries, keys and values. The shape is fixed, but inside that all the weights will be randomly initialized, because in the back propagation all these weights will be updated. Think in that specific way. Okay. Okay, guys. Now next step. Okay. Now next step. Okay. Now let's see. For this thinking word, we have generated X1, Q1, K1 and V1. For machines, we have X2, Q2, K2, V2. Now the next step is that for each and every word, what we are going to do is that we are going to multiply this Q1 and K1. Okay. Now for this, you can see that over here Q1 and K1 has got multiplied. Okay. For this word, you can see that I have multiplied Q1 and K1. So here you will be able to see these two values is getting multiplied over here, Q1 and K1. Okay. Then for this same word, this Q1 and K2 will also get multiplied. So these two words will also get multiplied. So now you have two values, that is Q1, K1 and Q1 multiplied by K2. Okay. For the same machines. Okay. This is with respect to the first word. With respect to the second word, again you will be seeing that Q2 and K1 will first of all get multiplied like this. Q2 multiplied by K1, and then which is nothing but some value you will be getting, and Q2 multiplied by K2. So this two operation will take place with respect to the machine word, but with respect to the thinking word, this queries will get multiplied by keys of both the words, and this value you will be getting. Okay. So this value is called as score. This score you are actually getting. Okay. This score you are actually getting. Reason for Q1 and K1 multiplication, I'll tell you. Just second. Just wait for a second. We need to find out these words, right? These words which are the most related words. The problem in the attention model, you understood that, guys. We were trying to find out whether it is referring to the animal or it was referring to the street, right? Whether it was referring to the animal or whether it was referring to the street. Now in this case, I'm just trying to find out whether thinking is basically referring machines or if it is referring some other words, right? So for this, I will be first multiplying queries and keys. I'll get some value. I'll tell you after this. Now with respect to my machines, in that whatever keys were there, I'm getting 96, and here I'm actually getting 112. Okay. So this is basically my second step where I will be creating my score. My score for each and every words. How? By multiplying your queries with all the keys. Okay. Queries with all the keys. Okay. What if there were 3 words? Again, 3 words again. What is very simple, guys? If there are 3 words, you'll be having this Q1, Q2, Q3 again, right? See, if you are having word 3, suppose if I say I'm having a word 3 like go. So again, go will be your x3 word like this. This will be x3 512 dimensions. Then for this also you'll be generating Q3. For this also you'll be generating K3. Okay, and finally you'll be generating V3. Simple, right? And again, now this operation, how it will take? First Q1 will get multiplied by K1, then Q1 will get multiplied by K2, then Q1 will get multiplied by K3, right? Now Hulfrage is asking, sir, can you explain what is neural network? Hulfrage, just go and check my deep learning playlist, okay? Complete deep learning playlist. Now we are too much in the advanced stage. If you really want to see some old videos, you have to go back, okay? So I hope everybody is clear, guys, right? Now let's go to the step 3rd. Now what will happen after this, that we are trying to understand, okay? That we are trying to understand. Now in the next step, I'll again rub this because I don't require this, okay? Perfect. Now in the next step, what will happen? In the next step, you saw that we have computed the score, okay? We have computed the score. Okay, we have computed the score. Now in my next statement, I am going to divide by 8. Okay. Why we are dividing by 8? Because understand, guys, as I told you that we have 64 dimensions in this, right? We have oops. Sorry for that. Okay, we have 64 dimensions here, right? We also have 64 dimensions here. Now in the next step, whatever Q1 and K1 we are getting, or whatever Q1 and K2 we are actually multiplying and getting, for this word, we will divide by 8. What is this 8? 8 is nothing but root of dk. Root of dk is nothing but, this is basically treated as dk, okay? Queries. What is the dimension of the queries, okay? And when I do the root of 64, I'm going to get 8. So here you will be seeing that we are dividing 112 by 8. We are dividing 96 by 8. So here you can see that this is my word 14 by value 14 and 12. Okay. Now this is basically my step 3. Now in the step 4, I'm actually applying a softmax activation function. Now this softmax activation function, if you don't know about softmax, guys, whenever we have some multiple categories like this kind of value, you can see that 14 is definitely greater than 12, right? Now softmax, usually whenever you give any inputs to the softmax, the value, the total value will be equal to 1, okay? If I do the summation of all the values that it is giving as an output. Now since 14 is greater than 12, the higher value that you have got is for 14, like 0.88, okay? And then the lower value is basically given to 0.12. But the interesting thing is that whenever you add this, the value is always 1. If you have 3 words, again, trust me, in this particular softmax will be giving us 3 values. But again, the summation will be equal to 1. Why softmax? Why softmax? Because understand, we are trying to find out the most important words based on probability, right? For thinking, if you are trying to pass through the softmax layer, you'll be able to see that based on this score, the highest importance is given to this. Then the second highest importance may be given to this. The third highest importance may be given to that, right? So it is pretty much simple, guys. Just try to understand with respect to that, okay? Krish, we are not able to understand why we are dividing by the root of dimension. In one of my interview, I got this question. Because this is based on the research paper, guys. They had research with different values, but they were able to derive it when they were considering this query size. This query size was 64 dimensions. They were just trying to use it as an hyperparameter, and they finally used this as square root of 64. That is what it is mentioned in this particular blogs also. Okay. So this is a kind of hyperparameter, guys. This 64 dimensions, 8, you can see it has simply taken root of d of k. So d of k is basically your dimension. Okay, so have everybody got clear with these 2 steps, guys? With dividing by 8, root of dk, and the other things. Everyone, can I get a quick yes? I hope you are able to understand it. I hope you are able to understand it properly. right? Everybody is able to understand, guys? Just give me a go ahead quickly. Yeah. Guys, are you liking, or you think that you're not able to understand from my explanation, something like that? I will try to improve it more. But just understand, we are just going step by step, right? Okay. Now, what is the next step? Okay. Now, next step, you can see that we have applied this softmax. We are getting this value and this value. Okay. This value and this value. Yes, yes, yes. This would be available. Yes, this would be available in the deep learning playlist, guys. It is a continuation of the previous live session. The thing is that I will try to cover BERT also after this, and probably will be using Jay's blog only. Again, he has written in an amazing way. I told you, right? Here it is. Everything is available here. Some amazing thing he has run. Visual guides to use BERT for the first time. Illustrated GPT-2. Amazing blogs he has actually written. You also see his QCon London. He has given the talk. It was amazing. And I just saw this today. It was very, very good. So I don't understand what is query keys, values, and why we calculate them. To provide the self-attention. I told you, right? Here, now I'm getting 0.88, 0.12. Definitely, I know thinking. Whenever I consider thinking, the first importance is gone to this particular word. Then you can see the next important with machines. Suppose you have multiple words like that, right? Okay, now, in short, what is the next step? Okay, that we are trying to have a look. Now, in the next step, what happens is that, guys, okay. Now, in the next step, whatever the softmax value is there, right? We have still not used these values, right? This values is multiplied by the softmax value, and we will be again getting a different vector. We'll be getting this different vector. And for this particular word, you will be having vector v1, vector v2. And finally, we add these two vectors to get z1. Now, you may be considering, Krish, why we are multiplying this value? Understand, guys? Sometimes researchers, they try to continuously research various things. And they try to use some of the other parameters. And indirectly, you'll be seeing that internally, due to the multiplication or due to the addition of those things, it works obviously well. Right? So here, this is one more thing, because these values that we have created, it will just not go for waste, right? Somewhere we have to use. So this softmax value is multiplied by this value, and here we'll be getting v1 and v2. This v1 and v2 will be added, and finally we get this z1. Okay. So here you can see that all this particular operation is the final step. Here you are actually multiplying softmax multiplied by value. You are getting vector v1 and v2, and then you are basically getting the sum z1 and z2. Okay. So here, with respect to this, z1 will be the output of the self-attention layer when you are passing thinking, and this z2 will be the output of the machine word when you are passing through the self-attention. Okay. So this was about this particular step. I'll rub this. So you can see that, guys, simple over here. One more addition, one more multiplication is done, where we have multiplied these values with the softmax, and then finally I am actually getting this particular sum where we are adding v1 and v2. Okay. So and this v1 and v2 will also be giving you information about the other words, because here you are adding the values, right? You are adding the values. So finally you will be able to see this particular vector, that is z1. Okay. How many words are taken as input? Any number of words you can provide, guys. Understand, this works absolutely fine as a language translation for very, very big sentences. It works absolutely fine. Okay. There is not a problem with respect to that. Okay. Now let's go to the next step. So I have got my z1 and z2. Now indirectly, what type of multiplication is taking place, guys? So see, all these steps can be told or can be mentioned in this specific number of steps. So first you take the input, you multiply it by W of Q, you get the Q. Then you take the other input, the same input, you multiply it by WQ, and you get the K value. Similarly, X is multiplied by W of V, and you get the V. So Mukesh Kanan says, is there any window size like in attention model, sir? No, it is not. Okay, no window size. You can give, because all the words are going parallelly. Okay, all the words are going parallelly. Understand one thing. Okay, now this operation is this what we have discussed over here, right? We have discussed the same thing, right? So this, just by using these 4 steps, you can understand this. This multiplication will happen. You'll get Q, K and V. Now what is happening after that? You are multiplying Q multiplied by K, and obviously when you are multiplying these 2 matrices, you have to transpose one of the matrix. So in this case, I have transposed K of T. Okay, and then you have divided by root of D of K. D of K is nothing but your dimensions is 64, right? So on top of that, you have applied an activation function like softmax, right? You have applied a softmax, and then you are multiplying by V. Then finally you'll be able to see that I'm getting the Z value, right? Now in this case, what is happening? This first layer is your first word. The second value is your second word, right? Now see this, guys. This is very important to understand. We have combined all the words. The first word is nothing but thinking, right? The second word, vectors, is basically machine. So we have placed all the words one after the other, and we are actually doing a matrix multiplication with W of Q, W of K and W of V. Right? If there are 3 words, then probably we'll be having one more vector. Sorry. I don't know. Suddenly this will change. Okay. Now, what is happening over here? If we have one more word, so I will try to add one more vector over here. Right? One more vector, which is, again, this all dimensions will be 512. Right? This will be a 64 dimension. Now you can think that what dimensions will come over here. Right? So this will be a third word. Third word, suppose if I say go. If you have 4th word, again we'll stack it one after the other. And by this, we will be able to do this matrix multiplication very easily. Right? Matrix multiplication, that is our main aim, right? We don't have to just wait. Here we are giving all the words at once. Are you getting it, guys? Everyone? How can we create weights of key values and queries? We just have to provide the size, guys. The weights initially will be initialized randomly. Remember this thing. It will be initialized randomly. Okay. Now, if you don't know how to initialize weights, just go and check my deep learning playlist. Because in the back propagation, this weights will be updated. In the back propagation, this weights will get updated. Yes. So this weights are going to get updated. This all weights will be updated, because understand, once whole from encoder to decoder it goes, over there we'll be computing the loss function. Based on the loss function, we'll be creating an optimizer. The optimizer work is basically to reduce the loss function by updating the weights. We need to update the weights. Right? I hope everybody is clear. I think everybody is clear with this. Yes, key, weight, everything. Those values are basically learned during the back propagation. Again, guys, it is very, very difficult to just visualize it. So I'm following this particular diagram, which will actually give you an idea. Again, there are a lot of things that happens internally, right? Each and everything is very, very difficult to just specify what will happen after that, how that value is actually updated, many things. Okay. How to choose W and W of K. It will be initialized randomly, guys. This will be updated in the back propagation. Always remember that. Okay. Don't get confused. Just read the research paper. You'll be able to understand. Okay. Fine. Let's go to the next step. So I hope everybody has understood and we got the final Z value. Now, one problem with this. What is the one problem with this? Now, guys, you remember that we are actually using, you can see in this, just a second, if you go up, okay, we are actually using one W of Q, one W of K and one W of V for all the words. Okay, for all the words, right? Are we passing words as a single input or sentence? See, guys, in sentence there will be many words, right? Each and every word will be converted into vectors of the same dimension, that is 512 dimension. It will be stacked one after the other. Okay, and it will be going. So coding I have not yet posted, guys. In the upcoming session, coding will also come. Okay. Now, what will be the next step? Now, see this, guys. Whatever inputs we have used W of Q, W of K and W of V. These are my vectors. And we are just use same weights for all the words, right? So we can basically say this as, we can indicate this whole WQ, WK and WV as something called as, you can see that a single head attention. Okay. So this, if I'm considering this three matrices, this three weights for the for all the words, we will call it as single head attention. But understand, by using just single head attention, what will be the problem? Now in this case, when I applied a single head attention, you can see that for it is getting, the importance is given to words like animal, right? But if I consider some other words like tired, because tired is also being represented by this it, right? It is basically representing animal. Tired is also represented for the animal. So here in this case, you can see that the line is very, very light, right? But we should also get something. We should also get some importance for this tired word, right? And right now we are not able to get, because we are just used the single weights, and these are the same weights for all the words. Now what if I use multiple weights like this? Okay, multiple weights. This is just your single head attention. Instead of single head attention, we will try to use multi-head attention. So multi-headed attention basically says that in this case, we will try to use head 0, like this will be my weight 0 Q, weight 0 K, weight 0 V. This will be my weight 1 Q, weight 1 K, weight 1 V. Suppose if I am using two heads, so I can say attention head 0. So this will basically be my attention head 0 weights. This will be my attention head 1 weights. Okay. This will actually help us to indicate or find out the importance of the other words, or how familiar that particular word is, right? Now in our case, when I was referring to that particular sentence, it was just getting referred to animal, but that it is also should give some importance to tired. But since we are just using one head, if I am considering this WOQ, WOK, WOV, I will be considering this as one of my head. Right here in the back end, you will be seeing that this weight is getting used for each and every sentence, each and every words, right? So what if we have different attention head for different words, right? So here you can see that I have my attention head 0, I have my attention head 1. In this, my queries are basically indicated by Q0, Q0, K0 and V0. Here we have Q1, K1 and V1. Okay, so like this, how many heads we will be considering? So here again, based on this, they have told we will be using 8 heads. We will be using like this 8 heads. Now when we use 8 heads, that means we will be getting 8 Z values. Okay, this is with respect to one head, right? We are getting one Z value. But what if we use 8 heads? So we will be getting Z1, Z0, Z1, Z2, Z3, Z4, Z5, Z6, Z7, right? So like that, you'll be able to see that now we are passing it through 8 attention heads. So I'm finally able to get Z0, Z1 till Z7. Now still, it is not just the end, because I told you as soon as we pass the input to the attention model, I should be getting one Z1 value, right? But there I have 7 Z value. 8 Z values, Z0, Z1, Z2, Z3, Z4, Z5, Z6, Z7, Z8, Z8. How do I combine them so that I actually form Z1? Okay. So for that, the next step is basically, you'll be seeing over here, we will try to combine this, all the Zs. So here you will be able to see that we are combining Z0, Z1, Z2, Z3, Z4, Z5, Z6, Z7. After we combine all those things, guys, again, before passing it to the feed forward neural network, we will again initialize another matrix. This is in the case of multiple attention heads. Okay, we will initialize another matrix, and this matrix will get multiplied by all the concatenation of this attention heads, and finally we will be getting a Z value. Then we can forward it to the feed forward neural network. Okay. So why, and again, this W0 weights can also be updated in the back propagation. Okay. Understand this particular thing. I hope everybody is clear till here. Right now we are still in the encoder layer, guys. Okay. We are just understanding these two things right now, because the same thing will happen in each and every layer. We are just understanding till here. We have come up till here. we have calculated Z1. Similarly, for this word, we have calculated Z2. Okay. So now we will pass this input to the feed forward neural network. Now let's see what will happen after that. And still we are in the encoder layer only. Just imagine, guys, how much effort he may had actually put, Jay. Okay, guys, so all good. It needs a lot of computation power. Yes, definitely it will require if you are training it from scratch. But now, right now, a lot of transfer learning techniques will be used. If you know about BERT, trust me, BERT is just one kind of transformer where you'll just be using much of the transfer learning techniques for most of the NLP task. So how many weights matrices are total? I think you have to search for that. I think there will be many weights parameter. If there are 10 words, which 8 words will be chosen? In case of 10 words, 8 words will not get chosen, guys. Just try to understand this thing. It will just multiply with all the attention, right, of all the words. Okay. Now, guys, this is the whole operation that is taking place. Here you have your input. Here is your attention head 1. Here is your attention head 2. Let me just denote it into for you. So here is your attention 0, attention head 0, attention head 1, attention head 7. Finally, you will be getting your key, queries key values, query keys values, query keys values. So here you have Z0, Z1, Z2. You'll combine all these things. You will multiply by this weight of 0 and finally you'll be getting your output Z. Now this will be passed to your feed forward neural network. Okay. Perfect. So let's go to the next step. Now what will happen after that? Feed forward neural network, I think it is pretty much simple for you all to understand. Now, okay, what is the importance of this? I was saying, right? Why we are using multiple heads? Now, if I go and see now, you'll be able to see that if I'm using a head, 2 heads, right? Now here you'll be able to see that I'm also getting the importance of tired word for it. And I'm also getting the importance of the animal word for it. Okay. So both the importance word we are actually getting. This is just for head 2. But if there are multiple heads, again, more importance word, whichever is more importance word, we will be getting highlighted that particular values. Okay. Now you can see that as we encode the word it, one attention head is focusing most on the animal while another is focusing on the tired. In a sense, the model representation of the word, it bakes in some of the representation of both animal and tired. Okay. Okay, guys. So the next step, now this is in case of if we add all the attention head to the picture. Suppose if we are adding 8 attention head, you'll be able to get different colors and different values with respect to 8. Okay. Okay. So guys, cool. All good till here. I know, see, sometime it may be difficult, guys, but you really have to read it once or twice. Amazing blog has been given by Jay. So I think you can just go through it, read it if you really want to be good, because implementation wise, it will be very easy. Okay. They will be specifically using libraries and all. All good, guys. Shall I move ahead? Okay, perfect. Now, fine. Let's understand one more thing. Okay, in this. Now, there is one more instance that we need to. There is one more thing that we need to take care of, guys. Sometime when we give words to the encoders after converting it into a word to vector. Okay. Now, in this case, you'll be able to see that I am basically giving this word, and I have actually converted word to vector, basically into a vector of 512 dimension. Now, before giving to the encoder, guys, there is a concept which is called as positional encoding. Okay. There is a concept called as positional encoding. This positional encoding is what exactly it is. Okay. Positional encoding. Now, this positional encoding will basically say that whether this word and this word are near, or whether this word or this word are near. Okay. Now, here you can see that the ordering of the words are also pretty much important whenever you are writing sentences. Okay. The ordering of the words. Okay. The ordering of the words is pretty much important with respect to any kind of sentences, right? So based on the ordering of the words, we will be providing some positional encoding. Okay. Positional encoding. This like suppose if we have JE Swiss, right? I will basically be able to relate this word will be much more relatable to this particular word because of the distance, and this distance I can provide it through positional encoding. Okay. Now what is this positional encoding? I'll just give you one example. Now see this. Now this is one example. We have given this input to this embedding by a vector. So this is of 512 dimension. And then we have applied some positional encoding. Now positional encoding, just understand that whenever we take these vectors, we are going to assign some vectors over here. Whenever we are assigning these vectors, and suppose this vector is there Swiss, right? And this vectors is there Etudiant, right? Suppose this 3 have been computed. This 3 positional encoding has been computed. You'll be able to see that if I try to find out the distance between this vector to this vector, this will be less when compared to this vector to this vector. Okay, because this basically says that how much distance, whether this particular word is the next word after this, or whether this word is the last word after this. So it is basically just calculating the distance of the word. Okay, so distance of the word, like how far it is, whether it is in ordered or not. But remember, the nearer words like this will be having this particular distance of vectors very, very less. Very, very less. Okay, when compared to the farer words. Okay, so that is the reason why we are using positional encoding, because the ordering of the words plays a very important functionality. Ordering of the words is important. Ordering of the words is also important, right? To find out which is the most important thing. Okay, so I hope everybody is able to understand this thing. So this was about this positional encoding, which is one more thing. And when this is happening when you are providing this as an input. When you are providing this as an input to the encoders. Before providing this to the encoders, you'll be able to see, before providing to this, you are applying a positional encoding and you're adding to these vectors, and finally you'll be seeing that you are getting some embedding dimensions with some time signals. Time signals basically means whatever positional encoding parameters or values you had, you are actually integrating in that by adding it with this embeddings. Okay, so I hope everybody is clear. This is basically handling the ordering of the words. Now let's skip this for right now. Now we are also going to understand some more things. Okay, now before it is passed to the feed forward neural network, guys, you should also understand one thing. Okay, after the self attention, we will be also applying something called as a normalization. We are also going to apply this normalization. This normalization is basically doing two functions. Now here you can see that one detail in the architecture of the encoder that we need to mention before moving on is that each sublayer in each encoder has a residual connection around it, followed by a layer normalization. Now what is this residual connection, guys? Can anybody tell? I hope everybody has heard of ResNet. If you go and see the ResNet architecture, suppose this is your hidden neurons, right? Suppose this is your hidden layers. The data will be passing like this, right? Sometimes it may happen that data of directly passing like this, it may pass to something like this. Like suppose these two are not playing, these two hidden layers are not playing that very good role. So what we can do is that whatever input is coming here, we can actually pass it to this particular node or this particular layer. Okay, like this is basically from residual connection. We basically say it as a residual connection where we can skip some layers if this is not important. Okay, yes, so we can skip this connection, we can skip this 2 connection and we can go directly over there. So similarly in this case we have, if this self attention is not performing well, what we can do, or if this self attention is not performing well, we can directly skip this and we can provide this connection over here directly to this normalizing function. It has to normalize. This is your layer normalization. Okay, layer normalization. And why this is used? Because understand, sometimes your self attention may not work well. It may not be that important. Yes, it can be same as dropout. You can also consider it as a dropout, or you're just skipping it. You are just skipping this layer. Similarly over here you can see the output of this add normalization. If this feed forward is not important, it will directly be passed to this add or normalize. Okay. Otherwise, if it is important, it will go in this particular path. Okay. So this is what is happening inside this, apart from the additional functionalities whatever we have discussed on the top. So what all we discussed, guys? See, First of all, we understood about encoders. We understood the operation of encoders with respect to self-attention, right? We understood there are keywords like queries, keys, values, so many things we have understood, right? And then we also understood about positional encoding, right? Positional encoding, if your words are in out of order. So we have done this. We have also understood about residual connection, right? Residual connection. So many things are there. Now just imagine if this blog was not there, I would not been able to understand this. I'm not that smart, guys. Okay, by seeing the equation, I can. I usually take time to understand things, but I would really love. Suppose if I go and see that particular blog, and if I don't understand the equation, I'll skip the topic, because for me to understand it will take time, and I have to put a lot of efforts, right, in that. And suppose if I'm not able to understand, I'll not be able to teach you also. So sometimes some of the videos will take time because I'll still be exploring it, you know. Okay, guys. So I hope everybody is clear with this. I will be taking all the questions at the last. Don't worry. Now let's go to the next step. Can I get a quick yes if everybody is able to understand? Is it good? Because the session has gone for more than 1 hour now. I hope you are not getting bored, right? Because you are learning with me. I think I'm able to make you entertain also. Perfect. I'll take up the question, guys. Don't worry. Now, what is this? Okay, I told you add and normalize. What this add and normalize does is that, see this. Add and normalize is nothing but whatever output I'm getting as Z, okay, I'm taking that, I'm adding it to my inputs, okay, and then I'm performing a normalization layer. Okay, this is what it happens inside. Okay, now this is altogether the whole architecture, guys. You can see the values is getting passed. Now, we still need to understand about the decoder. In decoder, what all things are there? Now, this is your encoder 1, encoder 2. I told you that obviously in our research paper, they have written that there are 6 encoders. But here the example is given of 2 encoders. And again, both the encoders are almost same. Here also you have residual connection. Here also you have the residual connection, right? Now, after this, the output of this particular model is passed to the decoders I told you. But inside decoders, what all things are there, we need to understand. Now, just let's see what are present inside decoders. That we'll try to see. Now, just compare with respect to encoder and decoder. In encoder, you have a self-attention layer. You have a feed-forward neural network, right? So here also you have a self-attention layer. You also have a feed-forward neural network. But in between, you have something called as encoder and decoder attention. Now, what is this encoder and decoder attention? This is similar to the self-attention model. This is similar to the self-attention, right? But the only difference is that the output of this encoder is passed to this. Is passed to this layer of every decoders. Okay, it is not passed from starting over here. Okay, it is not just passed to the self-attention layer, but instead it is passed to the encoder and decoder attention. And the encoder and decoder attention will be doing the same work as self-attention layer. Okay, only the input is basically getting passed to this through the encoder. Remember, the input to this is basically the output of the encoder. Encoder output is passed to this as an input. Okay, that is pretty much interesting to and it is very much important to understand. Okay, now this is done. Now here you will be seeing all the operation, but here you have to notice one more thing, guys. Just let me just show you one more very, very important thing that I forgot to tell you. Okay, I'll just rub this. I hope everybody understood what is the difference. The output of the encoder, this output of the encoder is passed to encoder and decoder attention, and it is also passed to this decoder too, again to the encoder and decoder attention pass. Okay, now if I consider this, here also we give some kind of input. Here also we give some kind of input. Now what will be the input? Let's see what will be the input. Now input, remember guys, the output of the encoder is given over here, right? Again, all this processing is done. We get the output. And after getting the output, first of all, we apply a linear and then we apply a softmax. After softmax, we get our output. Suppose I'm passing think. Thinking in Hindi is like sochna. Okay. So I'll write sochna. Okay. Now this sochna word will again be passed as an input to my self-attention layer in the decoder. Okay. So this will get passed Sochna. In the first instance, I'll pass Sochna over here. If I'm converting English to Hindi, okay, this Sochna word, I hope I have written right, guys. My handwriting is bad, okay. So I am actually passing it to my self-attention model again. Again, when it is going up, it will get combined with this next output. Because after this, we have to find out the next word. Remember one thing, guys. Here we are providing all the parallel inputs, right? But here the output that is getting generated, it will be one by one. Okay? It will be generated one by one. Again, try to understand this. Here we passed all our input at once, but here we will be generating our output one by one. So in the first case, basically my encoder output gave this, it went over here, it converted into Sochna, okay? But after Sochna, I have to generate the next word, okay? Next word. So what this will happen, this will go again over here as an input. Now this input will get combined with the output of the encoder over here. Again, decoder attention will happen. Again, all the process will happen. Then you will go to the linear and softmax, and then that machine will be converted into something like yantra. Suppose anything. Okay, guys, it is up to you. Okay, whatever you want to use, machines for Hindi, whether you want to use yantra, whether you want to use something, okay, just it will get converted. Now in the next step, what will happen? Sochna will also get passed and yantra will also get passed. Okay, because these two words will now be responsible in finding the third word along with your encoder output. Along with the encoder output. Okay, along with the encoder output. And remember, again your input will not be going. Okay, again your input will not be going. Input has gone at once, but this operation will happen again and again unless until you don't get your EOS, end of statement. So it is similar to sequential sequencer, right? In sequential, we only use the final context vector from yes. Yes, everything is almost same. Then go to your third word. Then your third word will again pass to this. Again, all these particular steps will happen. And again, these things will actually happen. Guys, have you understood this or not? Just tell me, everyone. I think I've never taken so long a session, but have you understood this or not? We'll try to complete this. This is important. Trust me, this is very, very important. Right? Let me rub it. Okay. Everybody clear? Yes, guys, sometimes you may not be clear exactly, but I would suggest that just try to have a look and read this blog along with the research paper. Now see this. Let's see on the decoder side how it works. Okay. So at the time step 1, you can see that I have given my input. Embedding has happened. We are embedded with time signals by positional encoding. Now we get the output over here with respect to the encoder. Okay, with respect to the encoder, you can see over here we got the output. Now this output is basically passed as a output to a decoder and decoders over here. Finally, we get the output, and in the first instance, I get I. Now this I will again be passed to the decoder. Okay, again it will be passed to the decoder, and this sentence will again not be passed because that value is there. Okay. Now here you can see in the second instance, you can see that the first output I is getting passed as a vectors over here, previous output, and here you have M, again some positional encoding is getting applied, then all these getting values are getting converted. Okay, so see this whole operation. So we will send decoder model also parallel. So how? No, it is not getting passed parallel, one by one. See, at time instance 2, I is got passed. M is generated. In third time instance, M is getting passed. Then you are getting the output over here A. In the fourth time instance, A is basically passed. You get the output student, right? In the fifth, you can see student is passed, and this is basically your end of the statement. Okay. So I'm telling you guys, this blog is amazing. I really want to thank Jay, okay, for this amazing blog. He has written, I don't think so like anybody could have written this. invested so much time and written this, right? I would definitely not. I would not been able to do it. And trust me, so much efforts is there. His YouTube link is given in the description, guys. Just follow him, okay? Subscribe his channel, because Bert also will try to discuss with respect to this. Now, the final and the softmax layer, you can see, guys. This is how the log probability will be coming, and based on the probability, you'll be getting the value, okay? So here it is all, guys. And again, you can read all these things. And this is how amazing this is. This whole thing is. And so why self-attention is not working well? No, it works well. It works well. But remember, transformers work better than that. Okay. It works well. But this is a state-of-art algorithm. Okay. This is state-of-art algorithm. So please go quick shout out to Zay. Subscribe his channel, guys. It is pretty much important that, again, and you'll be able to see this, guys. Attention is all you need. They have done dot product attention, multi-head attention. So this is how they have actually shown in the research paper. Same type of operation, softmax of Q multiplied by K of T divided by root of D of K multiplied by V. Multi-head attention, concatenated head attention. This is there. So all these things are there. Self-attention, recurrent, convolution, self-attention. Everything is there. Okay. So let's read the research paper now. You'll be able to understand. But in the upcoming session, I think I will be including some examples, practical examples with the help of Hugging Face. There you'll be able to understand very nicely. But in the next session, we'll try to discuss about BERT. Okay, we'll discuss about BERT. BERT is there next. And probably again, I'll be referring him to through his particular lessons itself. Okay, everyone. Yeah, all good, everyone. Okay, perfect, guys. So I hope when will be the BERT? In a couple of days. I will be again keeping a session for that also. Okay, in couple of days mostly. Okay, guys. So I hope you have understood it, and thank you. Please do subscribe, share with all your friends, and please do follow Jay Alammar, guys. You will be able to see a whole lot of things from his. Okay. So if you like this video, please do hit like, share with everyone. That would be very, very helpful. Okay. Tomorrow interview, maybe. Let's see. Okay. How exactly attention model by considering the multiple head, how relations are extracted. Just read this once. Just read this once. Okay. Just read this once. I would request everyone to read this. Okay. Okay, guys. So thank you, everyone. Thank you for attending the session. I'll be seeing you in the next video. Bye-bye. So in a couple of days, I'll be also coming up with BERT session. Thank you, guys. Bye-bye. Ta-ta.